Okay, Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. So you guys can hear me. There's a sound check. Okay, good. Okay, so we are still in chapter 2, so which is the topic is a discrete time system. Okay, so last time we stopped at let's see. Okay, so last time we have seen that when it is a system, so we have characteristic of a discrete time system. So we are actually focusing on this four: linearity, time invariant, or time variant, causality, stability. Okay, and actually memory. We will look at this one also. Okay, but this is quite straightforward. And we have covered the first one, which is linearity. And why we need to check on that? Because this characteristic will, the first and second, the linearity and time invariant, actually to ensure consistency at the output of a system. Okay, so it's possible to have a non-linear system, but of course, designing that kind of system is more complex. And if we have a system which is linear, so we will have a simpler system. So that's will help a lot, okay, in designing the system. But then we have a causality and stability. So what are those? Those two are to ensure the practicality of implementing the system. Okay, so means that if we have an online system, if the system is not causal, we cannot implement it. If it's not stable, we cannot implement it. So we need to make sure if it is an online system, the system must be causal and stable. So we need to check. So if you have any system, then we need to check for causality and stability. And there are, I think there were several courses which you have taken last time. So already discussing about causality and stability. Either you remember it or not. So actually you did come through of this causality and stability topic last time because we have gone through several courses which is looking at a system. So whenever you have a system, we need to check causality and stability. If it's not causal, we cannot implement it. If it's not stable, we cannot implement it. So now it's just how are we going to check this causality and stability on a discrete time system? See, everything is actually just repeating things, just on a discrete time system only. Okay, so because we have covered linearity, so today we're going to cover time invariant, causality, and stability. And to overview the whole course, so actually we are here now, we are in week 2. Okay, so we are in week 2. So which is last week we have covered discrete time signal. So this week we are actually catching up a bit on discrete time system. So hopefully today you can finish the topic. So next week, so which is we will start our journey on what is actually the system that we want to design, which is what we call the LTI system. But before we go to LTI system, which is a linear and time invariant system, so we need to understand basic on what is a discrete time signal, discrete time system. What is the difference between signal and system? So that's actually what we what we did in this what we will do in these 2 weeks. So we will already know that what is a signal, discrete time signal. Discrete time signal is if we want to put it in equation, it's just a sequence of values. Okay, and we get that sequence of value from sampling process. Okay, and every value has its index. So that is actually discrete time signal. And when it is a system, so that is a signal. Signal is a sequence of values, okay, with index. System, it is an equation. So where you have input and outputs and a process, okay. So there is a process. So when there's input, output, and process, so that's what we call a system. If it is just a sequence of values, so that one is a signal, right? Okay, so let's see. And I did ask every one of you to watch some video, which is actually very related to our class today. This one. So this is actually about time invariant or time variant. Okay, either a system is time invariant or time variant. Okay, so do you guys have watched the video? This is a very short video. What do you find from this video? What do you understand about it? Can someone please explain a bit? Either from the chatting section, you can write it there, or you can speak through your microphone. Let's see, what can you understand? This is actually from signal and system last time. So, okay, because when you look at the signal, everything is actually analog. Everything is analog. This is not discrete. Okay. Anyone? Can anyone? What is actually time invariant and time varying? From the video, this 2-minute video. No one? Watch the video. So how many we have here? 28. So everybody still not active. So who can answer it right? I give you 1 bonus mark. How about that? Do you want bonus mark? 1% over 100. Give you 10 more seconds. Golden opportunity.
Amplitude.
What is that, amplitude? That's a very short explanation. Anyone? Depending on the system used to process the input signal, the output will be different. So actually both are those things. Depending on the system used to process the input signal, the output will be different. Still not accurate. I'm missing some keywords there.
What I can observe from the video is that if you change something such as the input time shift or output time, you can get either a system time variant or an invariant, especially if it's maybe if the input is similar to the output, it will be variant.
So which one? Which one? If it is a time invariant, so how is it? How will be the output?
I'm not sure. I know it changes if you set some parameter.
So this is actually just a revision from your signal and system last time.
Yeah.
Okay, okay, it's okay. So no one get the 1%, unfortunately. Okay, so it's okay. So we're going to revise everything back, but of course, in terms of we are looking at a discrete time signal and system. Okay, so we have seen linearity. So linearity is something like it needs to obey superposition principle this time. So I already give one analogy when you buy something at let's say some shops. Okay, so if you buy one item, if it is 2 ringgit, if you buy 2 items, it's supposed to be 4 ringgit. That one is linear. But if you buy one item, 2 ringgit, but then buy 2 items, the same item, suddenly the price change, not 4 ringgit, it becomes 3 ringgit, then it's not linear. Okay, so that one is we are looking at the signal value, Okay, still remember, so we have 2 things. When you have a signal, a discrete time signal,
Sorry doktor, saya tak dengar. Doktor? Doktor, saya tak
Same here.
dengar. Doktor mute doktor punya mic.
Dengar tu.
Doktor tak dengar ke?
Maybe message him. DSP. I can't hear
Dr.
you.
forgot to stop.
Oh, that actually works. Raise your hands. Can't hear.
Okay, I'm not sure why I did click the microphone. So thank you very much. Thank you very much. So okay, I will repeat again. I'm not sure how long I've been muted.
Since you started drawing the thing, doctor.
Since you started drawing also.
Okay, all right. So I'm going to repeat again. This is the what we have covered before is a linearity, because we have seen these two things. We are looking at these two things first. One is a linearity, another one is a time invariant. So what are those? Those are actually to make sure or to check that our output of the system is consistent. Okay, the output is consistent, and to look at the output to be consistent, right? So we are looking at both the signal value, and the index. Okay, and what is index? Index is time. Index is time. So whenever I mention about index, so index is actually time. Because this is a discrete time signal, we are actually writing the signal as a sequence of values. Okay, we can write it as a sequence of value, or we can plot it. We can plot it such this. So this is actually the x-axis is index, the index. So which is the time. We call it discrete time, right? So linearity is actually checking on the signal value. Signal value is if let's say this one. So this is actually what we call the x0. This one, the whole thing here in this circle, this is the signal value. 3 is actually x1, and this is actually x2. So this is x3. Okay. And when we are looking at index, so this is just, okay, this is index 0, index 1, index 2, index 3, right? So we have seen about linearity on how to test this linearity. So if we have, let's say, 2 signals, and then you sum, and then do the process, or if you do the process first on each of the signal, and then sum later, sum the output, so you should get the same thing, YAN, YB, right? Exactly as the analogy, buying the item. So either you are buying one, or you are buying two, or you are buying two, and then buying two at once, or you buy one by one, you should get the price exactly the same. Okay, so if you buy one and then buy another one, you get 4 ringgit, each is 2 ringgit. But if you buy at once and then suddenly the price becomes 3 ringgit, then one is not linear. Okay, now, and we have seen some example on that one. So in time invariant, so we are looking at the index. When we say that we are looking at index, so actually we are looking at the time. And time is very related to what we call a delay. This one, a delay. Because any signal can be delayed. Okay, sometimes you are recording, just for example, you are recording sine signal or cos signal. Okay, just let's say that this is of course a very simple signal, cos signal. So let's say this is any signal that you are trying to record from some environment. Okay, or you are recording, let's say, a ECG signal. So it's not possible that every time you record, you will record at this cos signal at 1. Okay, which is sometimes maybe when you start recording, Maybe it starts here. But still a cause signal with delay. With delay. It is the same signal, but with delay. Okay, so this is when we are looking at time invariant. So we're going to look at the system. Either it can handle the delay. So if it is a time invariant, so means that it doesn't matter what is the delay, the output is supposed to be the same. Okay, but if it is a time varying, so actually it depends on when we are recording the signal. Okay, depending on the delay, so the output will be different. Okay, if we are going to put an analogy on the buying the item again, buying some items from shops. So it can be like if you buy some item, let's say 5 ringgit today. Okay, this one. You are buying this. You are looking at an item. Okay, you are looking at item today, but you don't buy that yet. Don't buy it yet. Wait. Delay is wait. Okay, you delay buying it. Wait for another 3 days. Why? Because after 3 days there will be a discount. After 3 days there will be a discount. So you are looking at it, and then you wait for it, and then after 3 days, because there is an some promotion, then you buy. It's supposed to be 5 ringgit, but after waiting after 3 days, so you buy. You only pay for 4 ringgit, right? But this one, you are looking at the same item today, and then you buy it today. You buy it today, okay? And you pay 5 ringgit, and then wait for another 3 days. So does the price change to 4 ringgit? It won't change. It won't change to 4 ringgit. It's still 5 ringgit because you already pay. Okay, so that's the time invariant. We are checking the system whether if we are doing it on a different time, on a different delay, so should we get the same output? Should we get the same output? And a good system or a simple system, right? It's supposed to be time invariant. It's supposed to be time invariant. When it is a time invariant, less parameter to be worried on. So because if it is a time variant, it change on time. So there are a lot of other parameters that you need to cover, right? It's not that we cannot have a time varying system. We can, no problem. But as much as possible, as we want a linear system, so we want our system to be time invariant, right? It doesn't change with time. So it doesn't change with amount, which is a linearity. It doesn't change with time, which is a time invariant. So that will be a very good system. Okay. So that kind of system, which is a time and linear, a linear and time invariant system, or in short, we call it LTI system. So we will look on that one next week. Okay, but this week we just look at on a general system first. Okay, let's look at one example. So let's say we have a yn equals to 1/2 xn plus xn minus 1. Okay, so this is what is the input? The input is xn. So we have input xn, and what is the output? The output is yn. Is there any process? Yes, the process is we taking one sample, current sample. So this is what we call a current sample. This is the previous sample. Okay, and then we're going to sum these two samples, and then divide by 2. Okay, that's a process. So because we have input, output, process. So this is a system, right? So then we know that this is a system. Okay, so in checking this thing, there is a note here. So we need to make sure that this txn minus d should be equals to yn minus d. So what is this? This one is a delay first and then do the process. And this one is a do the process first and then delay later. So to delay first and then do the process, we should do this. The xn minus nd. Okay. So actually what is this is whatever inside this bracket, whatever inside the input bracket, input time bracket. So this is the time bracket. Okay, this one. This is the time bracket. So which is, we are using a square bracket because this is a discrete time. This is discrete time. So whatever inside that bracket is actually time. Okay, so this is not time, this is some multiplier. This is a signal value, which is the whole thing, xn. But inside that bracket is time. Okay, so we are looking at on that one. So what is this? We're going to delay input by nd. So whatever inside that bracket, we're going to delay it by nd. So the first one, I'm going to remove this. The first one inside the bracket is n, so this is where we just minus with nd. Okay, but this one is a n minus 1, so whatever inside here, so then we just minus with nd. So this is what we get, 1 over 2 xn minus nd plus xn minus 1 minus nd. Okay, the second one, because what we do here is, it's like originally it is a yn, and then we change yn minus d. So what does this mean? So we are delaying the output. So this is a delaying the input. This is delaying the output. So when you do a delaying an output, so actually you are changing the n. From n becomes n minus nd. So whatever n that you see at this right side of the equation, change it into n minus nd, because we are changing it. This is n minus nd. So whatever n we have here, so we have n here, so change it into n minus nd. And then we have n here, change that into n minus nd. Okay, so that's how we can see the difference here. So here we just n minus 1 and then minus nd. But this one we are replacing the n minus nd. And because actually n minus 1 minus nd is actually equals to n minus nd minus 1, right? These two are equals. So this is actually a time invariant system. Okay, because after the test, if we do the delay first and then do the process, and we do the process and then delay it later at the output, so it gives us the same outputs. So it is time invariant. So this is what I have told you just now. So to test the txn minus nd minus whatever inside the input signal bracket, okay, the time bracket with nd. But to test yn minus nd, change all n, whatever n that you see, change into n minus nd. Okay, so there's a difference. Any questions so far? Can you is it clear what is the difference between minus whatever inside or and change all n? So that's a two different thing. Okay. Okay, let's see another example. So let's see. So because we will use this notation now. This is a summation, right? A very basic mathematical notation for discrete time signal and system. Previously, you've seen lots of integration, right? That one. And another one is differentiation. Okay, so that is actually very complicated to solve. So this is actually continuous. This is continuous processes. But in discrete, everything becomes very, very, very easy, very simple. This one just a summation. And what is this? So this is just a difference. Difference means you have two things. It's just like A minus B. Okay. At this time, minus maybe previous time. So maybe this time, the current time minus, let's say, a future time. So it is a minus. So every time becomes simpler. Okay, so that's why it's very, everything becomes very easy for discrete time signal. So hopefully everybody can get A because everything becomes much, much, much easier. Okay, integration becomes a summation because now you see everything using a summation in this course. You're not going to see this anymore. There's no d over dx, so everything will become just a minus. Last time in signal and system, you see there's what we call a differential equation. Okay, so that is a d over dx is differential. So now everything is just difference equation. Okay, so hopefully everybody realize that. So that's different. So that's why you're not going to see this and this again in this course. Everything we use this. Okay, this is a summation. So what is this? So this is a yn equals to the summation of xk, where k is actually from 0 up to n. Okay, so you need to know what does this equation means, because this is a quite basic. This is actually just yn equals to x0 plus x1 plus maybe up to xn. Okay, so how many items? It depends on the n. It depends on the n. Okay, so if this is a y0, then it is just a x0. If it is y3, so it's supposed to be x0 plus x1 plus x2 plus x3. Okay, so it is a little bit different. See, a different time, you have a different equation. But is this time invariant or not time invariant? Seems like if we look at this, seems like it is not. It is a time varying, right? Because every n that you will have a different equation. But let's see, we will do the test. So either this system where it is described by summation of k from 0 up to n of xk. So the first test will be txn minus nd. So what should we do here? So whatever inside the time bracket. Okay, you need to remember that. Whatever inside this time bracket. So minus with nd. So what is the time bracket? So this one. So this is our input. So this is the time bracket for the input signal. So you're going to minus this k with nd here. Okay. Should we do something to this one? No need, because this is not within the time bracket. Okay, so do that and then do some maths manipulation. So you do m equals to k minus nd, and then replace k equals to m plus nd, then replace again m and k to the above equation as below. So you get something like, finally, you get summation of k, which is from minus nd up to n minus nd of xn. Okay, I'm going to skip this. So later we look at this, because this is just a maths manipulation. So hopefully everybody can follow this. Okay, because this is just some exercise on your understanding on maths. Okay, maths equation. But finally we get this one. So the second test is we need to replace all n. Any n that you see, replace it with n minus nd. Okay, so this is what we get. So inside that bracket is a k. That one is not n. So the only n that we have is this one. We're going to replace that. So it becomes a k from 0 up to n minus nd. And if we are assuming this m and k is the same, okay, we can do that. No problem, because this is just some variable. So this is xk. This is we can put that as the same thing, right? So this is k up to m. Maybe I'm wrong. This is maybe k. This is not m. This is k. Okay, so what is the difference? The difference is the range is from 0 up to n minus nd, but this one is the range is from minus nd up to n minus nd. So it is not equals. It is not equals, right? This one is equals, but the range is not equals. So then this is not time invariant. or sometimes we call it time varying. Okay, we can also call it as a time varying, either one. So any questions so far? So we're going to look at another example. This is a more simpler example actually. So yn equals to x2n. So we're going to check whether it is a time invariant or time varying. Okay. Okay, so to do the first test, what is the first test? Whatever inside the time bracket minus with nd. So this is where we have 2n, then you minus with nd. So that's one, first test. The second test is whatever n that you see, replace it with n minus nd. Okay, so this is what you get. So this is a 2n minus nd. So it becomes a x of 2n minus 2nd. So, and when we compare, so this is not equals. This is equals to n, but this one is just a nd, but this is a 2nd. Then this system is actually not time invariant because it is not the same. Okay, let's see, doctor, on upper n, why it is not like k equals to n. Okay, let's me go back to that equation. Because sometimes I did some typing error. Yes, you're right. This one's supposed to be k. Okay, because actually I'm replacing all m here, becomes a k. Okay, so that's we can compare that this is k. Okay, thank you. So this is actually not m, this is k. So if you put it m here, so this one will be m. Okay, I'm just changing the variable only. Okay, so you can use any variable actually, no problem. Right? Any other questions? Actually, the example is it doesn't stop there. So, but hopefully you can look at the example because this example is actually this is using what we call a real value. Okay, if we put a real value, so later you look at it, so we can see that the output is different. The output is different. Okay, so because the output is different, it's not time invariant. So I'm just going to read this from the last two examples. The time invariant test is actually testing the system with input signal at two different delay values. First test with delay nd, second test is with delay 0. So this is actually from the previous example. So in conclusion, time invariant system can also be described as a system that produces consistent outputs even if the input signal is fed to the system at different delay or at a different time. Okay, because that one is very, very important. So because we do not know when we are recording some signal. Okay, so we have two more characteristic. So which is causality, and the other one is stability. Okay, so there are two more, and this another two is for what we call for practical implementation. So if our system is not causal, so we cannot implement it, especially on what we call an online system. So the system is live. Okay, so if it is an offline system, we might we still can somehow use the non-causal system, but most of the time we try to avoid that. Okay, the stability, the same thing. So if the system is not stable, actually we cannot implement it. We cannot implement it. So why? So let's look why. So what is a causal? Causality, a causal system means the system only involve current and past input values. Okay, so that's the keyword, current and past input values. So we can have three types of inputs. First one is a current value. So which is if we are looking at the equations, so the inside of the bracket, the time bracket, it will write only n, nothing else, just n. Okay, that one is a current time. Past value is when you see it writes n minus some values. Okay, future is when you see it is an n plus some values. Okay, so for example, this one. So this is the current value or current time, because we are referring it at n. So this is the current. And this one is actually past value, because this is n minus something, which is n minus 1 here. And this is also past value. And if we look at this example, this one, so we have a x n plus 2. So this is future. This is future value. This is another future value. This is current value, because nothing else, just n. And this is past value. So to identify whether the system is actually causal or not causal, we just need to make sure that in this equation, there is no future value. So straightforward, we know that this is causal. Okay, because there is no x n plus something. Okay, it's going to rain. And this one, obviously, actually, originally the system is written such this, which is yn equals to summation of k from -2 up to 1 of x n minus k. When you expand this equation, you get something like this. So we see this is a 1, 2 items, which is the future value. These are future value, right? So this is non-causal. This is non-causal. And how about this one? This one is time is only represented by the square brackets, right? So this is a square bracket. This is not within the square bracket. So actually, we don't really look at this one. So we just look at this one, right? So thus only current value are involved. So there is no past value, there is no future value. So it only involves current value. So the system is causal. Okay. So the rules is very simple. So if you see future value, it's not causal. If you doesn't see the future value, it is causal. So causality is important. Causality is important when dealing with online system, because the system does not know what the future value is. That's why we call it future value. It doesn't happen yet. It's not really happening yet. Okay. So thus, it is impossible to compute the unknown value. Right? So if you are now at maybe at 10 seconds, so suddenly the system says that you need to plus value at 10 seconds and value at 11 seconds, which is yet to happen. It's not happening anymore yet. So how do we know the value? We do not know the value. It is unknown. So then our system will crash. The system will crash because it doesn't know what to compute. It will hang, right? Because it involves unknown value. So that's why causality is important. So we need to make sure that it doesn't involve future value, right? So if we still want to do that, so maybe the best is actually we are predicting the future value. So we are predicting the future value. So there's some algorithm or some computation that we are predicting the future value, and then we add that future value into our equation. So into the system. We can do that. Actually, we can do that, right? But the system that we're going to cover for this course, the whole semester, we're not going to do that. We're not going to do a prediction. So we are going to focus on the causal system. Okay, everything that we design will be supposed to be causal, so that it doesn't involve future value. And this is the fourth characteristic, which is stability. So again, this is for practical implementation. If we If the system is not stable, even the name is quite obvious. If the system is not stable, so it's not good. Okay, it's not good. We need to make sure that the system is stable. So how do we define stability? A system is said to be stable if a bounded input to the system will produce bounded output. Or in short, we call it a BIBO, BIBO. Okay, we are looking at input and outputs. Input and output. Our inputs and outputs supposed to be bounded. So what does that mean? The signal value, okay, when I put it as a signal value, so you need to imagine that this is the y-axis, right? The signal value is the y-axis. The index time is on x-axis. So when we are checking the either is bounded or not bounded, we are looking at the signal value, which is the y-axis, right? So what is this? So this is the y-axis value. So it needs to be not equal to infinity, or sometimes we put it as a must be less than infinity. Must be less than infinity. Okay, must be less than infinity. So this is we're going to check our input. So if you have a system has input and output. Okay, so now you have inputs. Check the input. Is there any infinity value on the inputs? And then you're going to run the system and then check again. Is there any infinity value on the output? So if there is nothing, not in the input, not at the output, so the system is actually stable. Right. So if you found some one value which is either at input or output, which is infinity, then the system is not stable. Okay, so that's actually the basic. Okay, let's read this one. Stability is important for practicality because no computer or any digital processor can compute using infinity value. Okay, this is the same thing. Okay, sorry for the interruption. So, okay, so infinity. What is actually infinity? What is infinity? Do you guys know what is infinity? What is infinity? Can anyone define infinity? So what is it? What is infinity? Okay, Umar says yes. So what is actually infinity? Let's see, do you really understand infinity? Because when a system has infinity, so it cannot operate because it's not stable. So what is actually that infinity? So in terms of value, of course, if you do anything on your computer, you plus infinity, you get infinity. It's not even a value. So what is actually infinity? What is infinity? Anyone? Everyone already asleep? So there's 28 of you here. Yes, value that is too high to be computed. I'm not sure, isn't it maximum number human created positive? Endless. Okay. Yes, endless is true. Value is too high to be computed. It's true. That one is a more accurate value that is too high to be computed. So that's why every system might have a different infinity value. Okay. So because infinity is just a concept, it's not a value. So it's one value which is very high, which is a very high to be handled to that system. Very high to handle to that system. Okay, so let's say you have something like what is it? Maybe a washing machine. Washing machine, you have a motor, right? So you have a motor, and then the motor will spin. at certain speed. Okay, but because of the spec of that washing machine, so it can only spin maximum at, let's say, what is it? So maybe at certain speed, let's say maybe 20 kilometer per hour, just let's say something like that. Okay. So, but if it goes beyond that, it will blow. It will blow the circuit. Right. So means that if a value which is higher than that 20 kilometer per second, so that one will be infinity value to that washing machine. So that's why any value which is actually cannot be handled, too high cannot be handled to a system. So it is the infinity to that system. Right. So that's why actually infinity is just a concept. It's not a real. It's not a value. It's not a value. Okay, so that's will be let's see some example here. What is memory? Memory is a system said to have a memory if it is consists of non-current input. So a system that consists only current input is called memory-less system. Okay, so if the system only involve n only, doesn't have a past value, that doesn't have a future value, that one is a memory-less system. If not, so it is called a memory system. Okay, let's try on quiz 1, just checking whether this is a signal. So how do we know this is a signal? Because we have two things now. One is a signal, another one is a system. So the question here is the signal bounded or not? Okay, means that is this signal will create or will have infinity value or not? Okay, bounded means that one. So when you look at these equations, so look at it carefully. So none of it is actually a system. Okay, so this is a signal which is described by some equation, and most of it is actually described by a basic signal. So which is one is impulse. This is impulse. This is impulse, and this is step signal. Okay, impulse of a step signal. Why this is not a system? Because it doesn't have input and output. So it just have some equation representing the signal. Okay. So it's not because there is no yn. Okay, because it doesn't have input and output. So it's just some representation of a sequence of value. Actually, this is a sequence of values. Example, this one is xn equals to un. What is the sequence of value? If you can generate a sequence of value from this equation, means that actually this is a signal. What is a U0? So this is a unit step. Unit step is everything 1 from index 0 until infinity. Okay, so actually this is equals to 0, 0, 0. Sorry, not 0, 1. 1, 1, 1, 1 until infinity. From 0 up to infinity. So these are actually the signal. Okay, so is it bounded or not? So can you answer this one, the first one? So what is bounded again? We are checking on which axis? So we are checking on y-axis. Okay, we're not checking on x-axis. So we are checking on the signal value. So is there any infinity value on the first one, xn equals to un? If we are looking at this one, so all this value, the value is everything 1. So there's no infinity value. Okay, means that this is bounded. This is bounded. Second one, xn equals to delta n. So this is impulse. And impulse is even a simpler signal because it is just a signal. So which is only have one sample. And that sample value is 1. So obviously this is bounded. only one sample. This one, you have an infinity number of samples, right? This is infinity number of samples. But all samples values are 1, which is, there's no infinity value. The infinity is at x-axis, not at y-axis. Okay, the third one. Okay, I'll let you answer this one. Number 3, is it bounded or not bounded? Can you get any infinity value on y-axis for number 3? So let's see. So please answer that. We're going to do this, and then we're going to do another one, and then we will end the class. Okay, we do another 2. Anyone? This is a k delta n minus k. So we have k there, and then this is a delta which is impulse, and have some delay. Is it possible to be unbounded? Or it's not possible? Everything will be bounded, value only. Try it. I'm waiting. Unbounded. Can k be infinity? Yes, actually k can be infinity because this is just some variable. It is some variable. So it is possible to be infinity, k. Okay, k is possible to be infinity. So now, is it bounded or not bounded? So there's a question, what is delta again? Step input, I think already answered that. Step is actually a value of 1 from index 0 up to infinity, but impulse is just a delta. This is delta. Sorry, this is delta. Delta is just, we have a 1 sample, which is, the value is 1. Okay. Unbounded. Okay, so that's actually true because when k has a possibility to be infinity, then the signal value can be infinity. Okay, let's do another one. Okay, the last one, 11. No, this is almost the same with that one. Okay, number 10. xn equals to 0.2 n minus 10 un. Okay, so this is un. This is delta n. Bounded. Okay, someone Rifat says bounded. Okay, bounded. Is anyone says unbounded? 0.2 n minus 10 un. N minus 10. So if it is bounded, what is actually the highest value? Okay, when you say it is bounded, okay, so maybe we can estimate what is the highest value. The highest value is not supposed to be infinity. Not supposed to be infinity. So what will be the highest value? Zero. Okay, let's do this. Is that correct or not correct? Okay, is that accurate or not accurate? So let's check that one. We have a xn equals to 0.2 n minus 10 of a un, and we already know that. So this is un. Okay, this is un. So everything is 1, but we start index from 0 up to infinity. So means that this one, we can also say is that this is actually 0.2 n minus 10, where n is actually from 0 up to infinity. Okay, if we remove this one, we can conclude that, so this is actually 0.2 n minus 10, where the n is actually from 0 up to infinity. So this is where at x0, what will you get is actually 0.2 minus 10. Okay, which is equals to, this is at, we are looking at n x0. This is equals to 1 over 0.2 to the power of 10. So, and 0.2 to the power of 10 is something like, so what is that? Can someone do that on a calculator? 0.2, 1 over 0.2 to the power of 10. Okay, so actually this is quite a big number, but not infinity, okay? Right? Some big number, okay, maybe that number, 9765626, but not infinity. So this is still bounded. Okay, and then if we check the last value, which is x infinity, so this one becomes 0.2 to the power of infinity minus 10, which is just almost like 0.2 minus to the power of infinity. And this is actually very close to 0. Okay, so that's a proof, which is the highest value is somewhere maybe 900,000 something. And the lowest value is actually 0. So this is something like an exponent signal, right? And this is not infinity. And this is very close to 0. Okay, that's the proof. So this is a bounded signal, right? And do not confuse when we say bounded. So bounded or not bounded is on signal. It's not on system. System is either linearity, linearity, time invariant, causality, stability. Bounded or unbounded is for signal, not for system. Okay, but if you want to check whether the system is stable or not stable, we are checking on the signal. We are checking on the signal. So does the signal bounded or not bounded? Okay, so any last question? Any last question? Is unbounded signal equals to unstable signal? Okay, another good question. Okay. Is unbounded signal equals to unstable system? Yes. Okay, actually it's not equals. It's not equals. The words, if you want to put it in words, unbounded signals will give unstable system. Okay, or will produce an unstable system. Okay, or we can say that if it is if the signal is input, unbounded input signal will give an unstable system. Or we can say that an unstable system will produce unbounded output, because it's either input or output. It's not just a checking on input or checking on outputs, right? So either the input is already unbounded, the system becomes unstable, or the input is actually bounded, but then the system change the input and produce unbounded output. So then we can say that the system is not stable. Okay, not stable. Right, but for simple, just a simple writing, just like such this, unbounded signal equals to unstable system. Yes. Okay. Yes. So if you want to put it on a proper wording, it's like what I'm just told you just now. Okay. Any other last question before we end our class today? So. Okay, I think no. So hopefully, okay. Next week, just to show this this thing. Alhamdulillah, we finish this discrete time system in time. So next week we will go to a new chapter, which is on LTI system. Okay, so this is actually a linear and time invariant system. All right, so see you guys next week on Tuesday. And just always remember that so next week is already week 3, so we will have a test 1 on week 5. So means we are very close now, very close to the first test. Okay, so Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. So see you guys next on Tuesday.
Terima kasih, Doktor.
Thank you, Doctor.
Thank you, Doctor.